Question number 83 from June 2020 mathematical science paper. Which of the following statements are true? So we will go one by one option. So let's first check with option 1. So Q has countably, so Q is the set of rational numbers, has countably many subgroups. So we will just prove it with a theorem. What the theorem states, let's go into that. So an infinite group has infinitely many cyclic subgroups. So what is saying that infinite group will have infinitely many cyclic subgroups, right? Since Q is infinite, so this set of rational numbers is infinite. Similarly, Q has infinitely many subgroups, right? So it has given in option 1 the Q has countably many subgroups, so which is incorrect. So Q will have uncountably many subgroups. Okay, so our option 1 is not the correct one. Let's check with the option 2. So this option 2 is the correct. Then okay, so Q has uncountably many subsets. Okay, many subsets we have. So cardinality of the power set of Q, so P of this Q within mod, we can write is the power set as a 2 to the power the set of rational numbers, right? So which is nothing but the LF null, that is the n0 equal to this 2 to the power node, 2 to the power this LF null is the continuum, that is the C. So Q will have uncountably many subset, right? So here our option 2 is the correct one. So let's check one by one option. So option 3 is every finitely generated subgroup of this set of rational numbers is cyclic. So here we will go with a result that states that every finitely generated subgroup of Q is cyclic. That every finitely generated subgroup of the set of rational numbers is cyclic. So our option 3 is correct in that sense. So if we consider, so we can just make it a proof that if we consider that G be a finitely generated subgroup of Q and let R1, R2 up to Rn this be the non-zero generators of G, and let us express Ri as Ai by Bi, okay, where AI and Bi are simple integers, and let S, you can write S is equal to 1 by summation J equal to 1 to N B of J, okay, which is an element of this set of the rational numbers Q. So then we can write Ri as Ri, we know that Ai by Bi, so it can be written as Ai summation of this J equal to 1 to N, where J is not equal to 1, J is not equal to I, B of I, so it will be Bi multiplied by 1 by S. So it follows from this expression that the elements Ri is contained, right? Elements Ri is contained in the group S, in the subgroup S, generated by the element S. So hence G is also a subgroup of S, right? So since every subgroup of a cyclic group is cyclic, we conclude that G is also cyclic. So it states that every subgroup of a cyclic group is cyclic, right? So here we can conclude that G is also cyclic. So option 3 is in our case is the correct option. What is the for this Q is isomorphic to Q cross Q subgroup. So we already know that Q, this set of rational numbers, and the cross product, the Q cross Q, they are not isomorphic as subgroups. So I'm not going into the details of the explanation. The proof is there, we can go into a contradiction, but this is what states that Q, the set of rational numbers, and the Q cross Q, they are not isomorphic as subgroup. So it is entirely the opposite statement is given. So this option 4 is also incorrect. So in our case the option 2 and 3 is the correct. Question number 84, that let SL2, so this is a group of 2 by 2 in the Z plane. Okay, so it is a matrix of 2 by 2 matrix A B C D, where M2 is a, we have to say that M2Z is the, it is a ring of 2 by 2 matrix, and the determinant is given AD minus BC equal to 1, and for any prime P, so let tau of P be another this matrix 2 by 2 matrix which belongs to this SL2 group, and we have the A B C D given over here. So out of the which of the following will be true? So the first option is saying that tau of P is a subgroup of this SL2. So let's take the consider that A1 B1 C1 D1 multiplied by dot product is A2 B2 C2 D2, which is an element of tau of P, right? So then we can write this A1 B1 C1 D1 A2 B2 C2 D2 inverse. So if we do this, what will be the inverse? So it will be 1 by A2 D2 minus C2 B2 multiplied by A1 B1 C1 D1, and we have done the inverse, so it will be D2 minus B2 minus C2 and D2, right? So here we can now, if we this take under the A1 B1 C1 D1 and D2, so it is 1, we know AD minus BC is 1, so D2 minus of B2 minus C2 and A2. So if we do the multiplication, so what we will get, so it will be A1 D2 minus B1 C2, okay, it will be C1 D2 minus D1 C2, that A1 B2 plus B1 A2, okay, C1 B2 plus it will be B1 C2, right? Now we have the conditions over given that A of mod A equivalent to the remainder of 1 mod P, D is 1 mod P, C is 0 mod P, and B is also 0 mod P. So these are the conditions given. So we can write from here. So A1 equivalent to 1 mod P. Similarly, D1 is 1 mod of P. C1 is 0 it is B1, right? Similarly for, so it is also A2, D2, C2, B2, right? So now we can simplify this. So if we write the same over here, the A1, B1, C1 and D1, okay, and we have the inverse over here, that A2, B2, C2, D2 inverse. So we can write it as A1 D2, right? 0, 0, each of the term will be 0 over here, and again it will be D1. Okay, since this A1 D2, we can write it as the 1 mod of P, and also D1 A2 is equal to this 1 mod P, and we have another condition, A1 D2 minus D1 A2 is equal to 1, right? So we can say that this this matrix is an element of tau P. So this tau P is a subgroup, tau of P is a subgroup of this 2 by 2 group SL2 set. So we can check with the options. So our option 1 is correct, it is a subgroup of SL2 SL2Z. So let's check with the other options also. Option 2, what is stating that X, okay, let's check with option 2. So tau P is not a normal subgroup, it's not a normal subgroup of the SL2Z, okay, it's not a normal subgroup. So let this X, we consider that X is an element of G, which is the SL2Z. We already know that tau with P is a subgroup of SL2Z, okay, and H is an element of H, right? So we have to find from here that X, H, X inverse, whether this an element of H in the tau P, this is a normal subgroup or not, right? We have to find this. So here we can do one thing, that X of H, X inverse, we just put the value of over here. So what is X? X is XY ZW, right? X inverse is W minus Y minus Z X, okay, and H is 2 by 2, that is A B C D. So if we put everything over here, the X value as X Y Z W, H A B C D is 2 by 2 matrix, and X inverse we will write W of minus Y minus Z X, right? So simplifying it, what we will get, so this will be X Y Z W, then do the multiplication, so it will be A W minus BX, no, yes, BX it will be, right? CW minus DZ minus of AY plus BX minus of CY plus DX. You do again the multiplication, what you will get? You will get this matrix, the X, Y, Z, W, and the inverse of it, that is W minus Y. Okay, you can do from here also, W minus Y and minus Z W. minus 8, it will be x. It will be x. Okay. So which is nothing but the 1 0 0 1, and which belongs to the is an element of h is equal to the tau of p we have already considered. So tau of p is a normal subgroup of that SL2Z. So in our case option 2 is incorrect because it's stating that's not a normal subgroup. So let's check with option 3. Option 3 is saying that it is the tau of p is at least 2 elements, and option 4 is the tau of p is uncountable. So let's first check with option 3. So we know that I is an element of the tau p if we, and this prime number is, we can consider it in matrix 1p p1 2 by 2 matrix, which belongs to the tau of p. So tau of p has at least 2 elements, right? So in our case the option 3 is also correct. Let's check with the has uncountable. So tau of p is uncountable, it is mentioned in the option 4. So let's check whether it is tau of p is uncountable. So we can write this tau of p as A B C D. This is a 2 by 2 matrix, right, which belongs to the, because we have to know this is a subgroup of this SL2, right? So where this A B C D is an element of Z, so each of these A B C D has only countable number of choice. Number of choices. So we cannot say that tau of P is uncountable. It is countable. So option 4 is also incorrect. So in our case the option 1 and option 2, these are the two correct options.